Hi, this is Terry Kuzma at Penn State University. Today we'd like to overview materials and nanotechnology. This is the introduction to nanoparticles and nanostructures, and this is part 2 of 2 in our series. So what we've done so far is we've looked at some definitions and examples and physical properties of nanoparticles. What we're going to review now is some optical properties. So we're going to look at briefly surface plasmons and quantum confinement. Then we'll go look at electrical properties, and then some quick links to health concerns. This material is covered in other courses within our offerings, so I'm going to go over this kind of quickly. So the optical property is the size dependence on the optical properties of nanoparticles is a result of two distinct phenomenon. The surface plasmon resonance for metal and the increased energy level spacing due to the confinement of delocalized energy states. And this is certainly most prominent in semiconductors. So let's take a look at a surface plasmon and do some definitions and hand waving to say how this works. Recall that metals can be modeled as an arrangement of positive ions surrounded by a sea of free electrons. So that's a consistent model that I discuss all the time in my material engineering courses. So what we have is we look at the positive charge. This would be our core atom, and then what it's able to do is allow some outer core valence electrons to be not actually individually linked to that particular atom. So now what we have is this really nice compact system, because we have the electrons holding together these positive per se ionized particles or atoms that appear to be in an ion state, positively charged. So this sea of electrons behaves like a fluid, and under the electrical field, it'll begin to shift. So we can see the electrical field here, and then what's going to happen is the electrons are going to move back and forth. So again, let's take a look at some pictures here to describe what's going on. If the electric field is oscillating like a photon, then the sea of electrons will oscillate too. These oscillations are quantized and resonate at a specific frequency. The oscillations are plasmons. And again, these oscillations are going to be set or fixed. I look at it as a tuned structure according to the area that's available on the plasmon. So if we look at the surface of the metal, we can see that the top, the air interface, acts as a dielectric. So this is the two sides of our system. And then what we have is the charge oscillating within the sea of electrons. So again, this is just another part B shows the same thing, that we can see that the electric field is causing the oscillation of the electron cloud that's on the surface of the plasmon to go back and forth. So a formal definition: plasmons are the current or the coherent excitation of free electrons in a metal. If the plasmon resonant frequency depends on the particle size and the shape and the material type, it's related by Planck's constant, as in semiconductors, energy. The surface plasmons are confined to the surface of the material. Optical properties of nanoparticles are dominated by the interaction of surface plasmons with the incident photons. So again, metal nanoparticles like gold and silver have plasmon frequencies in the visible range. So we'd like to use those for those particular materials because they're moderately easy to manufacture and they're moderately benign to biological entities. So they're used quite often for biotagging. When white light impinges on metal nanoparticles, the wavelength corresponding to the plasmon frequency is absorbed. The spatial locations, the spectral locations, strengths, and number of plasmon resonance for a given particle depend on the particle shape and size. And that's important. We're going to look at in a little bit how that would elicit unique colors. So this is the optical spectra of spherical. So again, I think that it not just to read the word and not pay attention to it. This is spherical. So this is uniform on all sides, so it's consistent. It's a sphere or a circle. So we can look at the optical absorption of the gold nanoparticles from 20 to 80 nanometers in here, and see what the emission is. And again, I think I recall this photo is not just gold, but it's also silver nanoparticles. So this shows that out of those two metals, we can actually get unique colors by controlling their shape. Not their shape is spherical, but controlling their size. So again, the discussion of the shape dependence, if we look at the optical absorption of the spectra, and again, I think I'd like to model this, or in my mind, I have an idea of looking at like a fish aquarium, and usually fish aquariums are rectangular. And if we would take a fish aquarium, and if we would oscillate it from the long side to the long side back and forth, then what will happen is water will, if it's full to the top almost, if we oscillate it, left and right on the longer length, sooner or later we're going to get a splash. And that splash is indicative of that length, of that dimension. If we would take it, that same rectangular fish tank, and oscillate it in the opposite direction on the short side, then in that oscillation we would actually get a different splash. So I don't know if that's a good analogy or not, but that's how I'd look at this. So basically, when this electrons are sliding back and forth across that material, to me they look like water in an aquarium. So depending on the incident light, when they give a splash or when they re-emit light, they're going to be a different color. So this is, you can see on the right graphs that represent this. So if we look at the incident light, then we could see that these actually emit at different colors. Again, this is due to the geometry. And again, in our past slide, this reference was to spherical gold. And right now what we're doing is we're taking a metal nanoparticle and we're making it a non-sphere. So in this case, we're looking at some kind of ellipse, and in this case, a triangle. And when we do that, we can get a different spectral response of the material. So this is, I think this plays in handy, because if we would look at this geometric shape or the triangle, the ellipse or the triangle, what we have in here is that these have a lot of charge on the surface, so they can actually be maneuvered in an E&M field. So basically what we can do is we can use this for a pixel like in a TV. So we can rotate the plasmon in a certain orientation, and then when light shines off of it, we would get a unique color. So basically what we can do is potentially move this material and then control its color response. So I guess in some ways there's things like this that have existed for a long time, such as LCD displays. They're that way too, that we control the position of the metal to control light emission per se, or reflectivity in an LCD, but completely different physics or system. But that's using that same analogy, what we're able to do now here with a nanoparticle is shine light on it, move the nanoparticle, and the re-emission of that light is going to be a unique color. So that would come in handy for say, computer screens, cell phone screens, etc. So we're looking at also plasma and optical properties, and we can determine the shape of particles, maybe by an SEM, etc. And what we can do is take these shapes, shine light on them. So when we would measure them, maybe in a UV spectrometer, that would give us a measurement, but not a physical measurement, but an optical response measurement. So we might be able to nominally call these things 50 nanometers based on some dimension from some point on here, but because of their geometry, actually their light emission is going to be different. So again, this is an interesting property of nanoparticles. Not only do plasmons possess the ability to emit light, but that dependence is also due to certainly the size, but also to the shape. So again, this is some more review of energy levels from as far as solid state physics. I think that these are going to be rehearsed in other classes thoroughly, so I'm just presenting them here for review. So this looks at the energy levels and semiconductors, and I think we're all aware of what this does. This tells us about the energy spacing, and certainly this equation links together the optical emission according to the band gap. So we can control the band gap, and then we can control the emission of the light. So this is how we would control for the most part the light emission from light emitting diodes. So we would control the band gap. So we can do this in different ways, and this is a direct band gap semiconductor, which is moderately easy to do. And then again, this is what we would say in for that comparison for bulk materials. I think that's everybody that would be watching this is well aware of that. But what we're doing is we have to control that to the nanomaterials, where we can actually modify the band gap in different ways, and we can do that with materials such as quantum dots. So the energy confinement spacing in quantum dots, so what does this mean? So quantum dots themselves, what we can do is we can change the band gap in a quantum dot, and when we're doing that, naturally we're changing the color of the quantum dot. So this gives us the ability to control that, and the quantum dot itself is very similar to the plasmon, which is generally thought of as a metallic material. But now we're using a quantum dot, and we're going to define that roughly, at least on the first iteration, as a semiconductor material, where we can control the band gap by controlling the relative doping within that material. So this is the energy spacing for quantum confinement. We can look at quantum dots, and I think this is cadmium selenide, the dots. So these are the relative diameters of the material and the particular light emission from that material. So this shows you the optical spectra of cadmium selenide quantum dots. So the EV that's necessary to give optical emission. So this is, again, just a review. So now let's take, again, some electrical property looks as we looked at mechanical, optical, et cetera, of these materials. And we're going to look further at, in another presentation, when I'm going to go over liposomes and cancer. We'll take a look at metal nanoparticles for biological applications. I thought it would be best to just keep it in that section instead of repeat it here, but I will cover that information in another presentation. So other electrical effects on the nanoscale we can have within the system. Surface scattering. We can certainly have changes in the electronic structure of the device. We can have ballistic conduction, discrete charging, tunneling and conduction, and microstructural effects due to the shape of the nanoparticle. So what surface scattering is, electrons have a general mean free path in solid state materials. The mean free path distance between scattering events such as charge carriers move through the material. As in metals, the mean free path is the order of tens of nanometers. If the dimensions of the nanostructure are smaller than the electron mean free path, then this surface scattering, not the scattering from the material, but actually the physical dimension, becomes a factor. So this shows you the two types of surface scattering, the elastic and inelastic type. This is the macro scale material here, where the distance is greater than the mean free path. In the elastic, the distance is less than the mean free path. And the inelastic, what it's going to do is scatter within that material. So again, when we looked at health, we have some presentations and other courses which cover this hundreds of pages thoroughly, but I just wanted to present some references since we're in this area just to be thorough. So, you know, there's causes for health concerns with nanoparticles because they're very similar in size to many biological structures. They're easily absorbed by the body. So typically, I think I discussed this probably in this presentation, I would say, and this is incorrect, but just a rough value, if I were to identify a cell size, and there's all different sizes of cells, but maybe an average size cell would be on the order of 10 microns or so. A red blood cell, 7.5 microns. But again, if we would look at that as an analysis, it's shaped like a platelet. So what are we measuring? So we're measuring the largest measurement on there, but it's a platelet. It's rather thin compared to its size, and these platelets are kind of like oscillating too. So my point is the measurement to say a red blood cell is 7.5 microns. That's a rough measurement too. So again, I'm going to say that a blood cell, or not a blood cell, but a generic cell would be about 10 microns. So we could see that materials on a scale of 100 nanometers would be quite a bit smaller than that cell. And actually, at the level of 100 nanometers or so, that's generally like a commodity that the cell would be able to process and move around. So generally, the portals on a cell are able to take in sizes around 100 nanometers, etc. Endocytosis, which is passing through the cell wall or engulfed by the cell wall, generally occurs at about 100 nanometers or less, somewhere around in there. So making nanoparticles there would be very good for medical reasons, but also it might be, on the other hand, very bad for biological or dangerous reasons. So I've always thought that these types of particles would be the type of particles like from cigarette smoking or mining, like black lung disease here was common in Pennsylvania. Pennsylvania has a lot of coal and iron. So these types of, or especially coal, this is why their steel industry was really important in Pennsylvania. So black lung disease was always a social concern around here. And I always thought that these were the particles that were able to get into a cell and cause problems, or the body was not able to evacuate. So these particles, or any particles on the order of nanometers, tend to act like asbestos. So that's a good model, and again, that's an analogy, but we have to be really aware when we're doing the manufacturing methodology that we don't want to especially inhalate through the lungs nanoparticles. And nanoparticles, because they're so small, they can be absorbed through the eyes. They can also be absorbed through the dermal layer. So nanoparticles themselves are rather dangerous because they remain suspended in the environment for extended periods of time, so they behave like a gas. So through, like, just per se Brownian motion, they never settle out of the air frame. And actually, probably most people would agree that the way that you would probably intake nanoparticles into your system, or probably the most popular pathway for that, would be through your lungs. So given that these nanoparticles behave like a gas, when we breathe, if we don't have appropriate, per se, filters, then we have the strong chance that we're going to be able to ingest nanoparticles through our lungs. So the health impacts of nanoparticles are really expected or theorized to be dependent on composition and structure, just like we saw for the optical emission. So these particles at a certain size, if they have even a different shape, they might be more or less dangerous to a person. So the potential health concerns are really unknown, but there's studies on here. The solid foundations, I think, are laid for these nanoparticles, but we don't have a clear picture. So the EPA here in the United States has a national nanotechnology initiative that provides funding to investigate these issues, and they have a lot of publications. So there's multiple facets of nanotechnology are available by going to the OSHA.gov site and type in nanotechnology safety, and there's volumes of materials that are available to look at these issues. So again, I'd like to thank you. That's the end of the presentation. Again, this was I don't know to say a bonus section, but I think this material was covered in part in other courses, but I did want to go over and give a quick review on this material because it linked nice with the other section that I was presenting. So I'd like to thank you for your attention and look forward to further discussions in nanotechnology, and we'll see you the next time. Take care.